How were geometry problems proven unsolvable by classical means? Imagine trying to solve a puzzle with only a compass and straightedge. For centuries, mathematicians believed all geometric problems could be tackled with these simple tools. But some puzzles just wouldn't give in. They resisted every attempt, no matter how clever the constructions. These are the famous problems like doubling the cube, trisecting an angle, and squaring the circle. People tried for hundreds of years, but these problems remained unsolvable with classical tools alone. The breakthrough came much later, with the rise of algebra and more advanced math. Mathematicians started translating geometric problems into algebraic equations. They looked at what lengths and angles could be constructed with compass and straightedge. It turns out that some lengths, like the cube root of 2, cannot be built with these tools. To understand why, think of the lengths you can create as solutions to certain equations. The classical constructions only produce solutions to quadratic equations, which involve square roots. But the cube root of 2 comes from a cubic equation, which is more complicated. It cannot be solved using just square roots, so it cannot be constructed with compass and straightedge. The same idea applies to trisecting angles. While some specific angles can be divided into 3 equal parts, in general it is impossible. This is because the algebraic equations involved are not solvable with just quadratic operations. Now, squaring the circle is a different story. It involves creating a length equal to the square root of pi. But pi is a special number called a transcendental number, meaning it is not a root of any polynomial with rational coefficients. Since compass and straightedge can only produce algebraic numbers, pi cannot be constructed this way. These proofs relying on the field of algebra called Galois theory, which classifies what numbers can be constructed with compass and straightedge. It shows that only lengths related to square roots can be built this way. Cube roots and transcendental numbers are outside this range. So, in simple terms, these classical problems are impossible because the lengths or angles they requiring are linked to numbers that cannot be created with just a compass and straightedge. The realization that these problems are unsolvable with classical tools came from translating geometric questions into algebraic language. This approach revealed the limits of Euclidean constructions and showed that some questions go beyond what the ancient Greeks could achieve with their compass and straightedge. It is a fascinating example of how modern math can explain why certain problems are forever out of reach using only the tools of classical geometry.